in a second here. Um, if you guys remember, we talked about short circuit calculation, overcome protection device coordination. The chapter 17 and 18, we're talking about overcurrent as well as short circuit and coordination and what's not. This chapter talks here about something very, very important. It's called equipment and conductor short circuit protection. When you have a conductor, you have to put a circuit breaker ahead of it. If you have an equipment, you have to put a fuse or circuit breaker ahead of it so you can protect these equipments and these conductors from being burned because of short circuit. It was explained to me one time, Derek, that a short circuit is, imagine a semi, huge semi going down 94 at 110 miles an hour. Shall we do that? Cops are not around. And all of a sudden, it hits a brick wall. That's what a short circuit. Can you imagine the impact with that? That's what a short circuit on a system like Dunwoody here, 3,000 amp, 480. That's if you go to the 3,000 amp switch gear, tie phase A to phase B to phase C, and flip the switch. That's what the impact is equivalent to a semi going down highway or interstate 94 at 110 miles an hour and hitting all of a sudden a brick wall. So a huge, you can see why it's important, guys. The damage, the amount of damage that could be that happen is huge. You burn equipment. Okay, so this equipment have to be rated to handle the short circuit for a certain amount of time. So that's what we're going to be talking about today, guys. And I can't emphasize the reason why I want to go over this chapter because it's directly related to the SKM that I want to be walking you shortly, guys, after. Directly related, the same topic. So understand the electrical equipment, they call it electrical equipment withstand rating, meaning how much can you withstand? How much can the electrical equipment withstand a short circuit and for how long before it basically turns into a big ball of fire? So that's what we're going to be talking about, guys, related to short circuit. Withstand rating, the same thing. Conductors also have something withstand rating. A withstand rating, guys, is you have a short circuit in the conductor. The conductor sits there and hold it. It's getting hotter and hotter and hotter and moving. And after, for there's a certain limit though, typically you're talking about cycles. For a certain amount of cycle, after that, you know what's going to happen? That conductor will completely burn, right? So that's called the withstand rating. National Code section Petraean 2 will talk about the interrupting rating, guys, and DC Code talk about the interrupting rating, the highest amount of current the short circuit device, like a fuse circuit breaker, can interrupt under normal, under test condition. Short circuit current limitation, ground fault, bonding, temperature limitation of conductors. If we don't care, what happens, guys, when you have a short circuit condition, the temperature starts rising inside the conductor. When you have a temperature rising inside the conductor, higher and higher and higher, what are you going to have? You're going to cook that conductor. Two things will happen. First, if it's insulated, the insulation starts melting. Second, if that's not enough, if it continues, that copper or aluminum conductor start melting. Can you imagine melting copper and conductor inside these conduits? That will. Can you guys imagine why we have conduits to start with? Now, if you're lucky enough, of course, the equipment only going to burn only your electric equipment. If you're not lucky, you just burned the building. You've just burned your building. So it's a big deal. Amp square. This is the term that they use, guys. Amp squared second, which is I. So I squared. So the amp squared second, I squared S. So they take the current, they square it. That will be a measurement of the amount of heat that a short circuit will generate. You're going to see this one in a second. There's calculation how much a copper or aluminum conductor safely can carry for a certain amount of period before it's damaged or destroyed. There's calculation. There's a term, and I know this is taking you guys to the next level. There's a term the engineers use, it's called damage curve for conductor. It will give you a curve and tell you this conductor under these circumstances can carry, so number 14, take 14. 14 guys can carry 15 amps for a long time, right? Or 12.5 amps for a long time. Double the amount of current on that. it can carry it for a couple of minutes. Now make it 1,000 amp, it can carry it for milliseconds. So it can carry it for milliseconds until the circuit breaker opens. If the circuit breaker does not open or the fuse does not melt, your conductor will start melting. Your conductor will start melting. So that's term that they use. They call it withstand rating for equipment or damage curve for equipment or conductors. A big deal. There are charts that give you guys the withstand rating. You are the lucky ones that we use SKM. This is iChat. SKM PTW. When you pick a cable in a second HUD, when you pick a cable with me, guys, every cable comes with a damage curve. What's a damage curve? It gives you the withstand rating of this cable. It tells you if you put this amount of current in this cable, it will last for this amount of seconds. If you increase the amps, it will last for lower amount of time. Every time you have a short circuit condition, you have two forces acting on your equipment, the evils. The two evil things, two forces. Two forces present when you have a short circuit or an overload protection. One of them is called thermal, that's heat. And the second one, gentlemen, is called magnetic. When you have a short circuit inside that panel there, this panel is being cooked. I call it shake and bake, right? You guys do shake and bake? You don't cook, Matt? Nobody cooks here. Derek, don't you cook shake and bake? Chicken, shake and bake chicken. Karen, you don't do? No? Oh boy. So that's exactly like shake and bake. So your panel is being shaken, physically, mechanically shaken by the force, the magnetic force, and baken by the heat generated by the short circuit. Now, what worse than that? Imagine every single component, if you have a short circuit system, a short circuit in your power system, every single component, part of the short circuit will be shaken and baken. For how long? As long as it takes the circuit breaker or the fuse to open. You have shaking and baking happening as long as the circuit breaker can open. So what do you need the circuit breaker to do? Open fast. So it stops the shaking and baking. Why? Otherwise, that thing is going to blow out off the wall, right? And burn itself. So that's the term that they use when they have a short circuit condition or ground fault. Shaking and baking. You shake it and you bake it. The baking, guys, happen with I squared T. That's how they measure it. They take the current, they square the current multiplied by the second. S is second time, and that's the baking. The shaking happen I peak squared, I believe. I peak. The I peak. Not sure if that's word now. I peak is the peak of the signal starts shaking the equipment. So anyway, you'll see it in a second. The last thing we're going to talk about, guys, is the tab rules. In particular, the 10-foot tab and the 25-foot tab. Tab rules is when you tab a conductor and you put an overconduction device more than the conductor can handle. So that's basically what we're going to be talking about, guys. Withstand rating, the most important thing, the term that you guys are going to hear about is always withstand rating. All the electrical equipment by manufacturer are labeled with their withstand rating, meaning for 3 cycles, 5 cycles, they can handle this amount of power. So withstand rating, guys, is a function of how much current they can handle and for how long. Energy. How much and for how long. It's not enough just how much. For how long. So they can carry the amount of electrical, that's why they call it energy, electrical energy for a given amount of, can I emphasize the word time, before what happened? Before it explodes. That's withstanding. The electrical equipment has the capability to withstand how much current, short circuit current, the equipment can handle for how long will decide the withstand rating of this equipment. The withstand rating of this equipment. Typically 5 seconds, guys, they give you a withstand rating for 5 seconds. After 5 seconds, your equipment can explode. Depending upon the damage curve, of course. So the manufacturers will specify the damage curve and will specify the overconduction device that you need to protect these equipments, guys. Air handling unit, chiller, what's not. The withstand rating of this equipment is this amount, and the short circuit is this fuse. So you have a short circuit, the air handling unit sits there being shaken, baken, shaken, baken. The fuse eventually will open. When you coordinate the fuse opening time, guys, with the withstand rating of the equipment, if you coordinate them good, then the fuse will open before the equipment burns. That's the whole idea that you guys are going to be doing with your friend Chad. what we call it the coordination. Your equipment will not burn. Okay. When you have a circuit, Karen, there are a few conditions for the circuits. Here's a circuit, for example. This is very simple, 24 volt circuit here with a 15 amp circuit breaker and a load of a 24 ohm. If you do the math, which you guys have done the math, there is also a resistor in the lines here, resistor in the lines, and resistor for the load here. So when you do your math, guys, you take the voltage divided by the amps, give you close to 10 amps. So you have a light burning at 10 amps, big light, or I don't know, a microwave burning until 10 amps, and at 240, the voltage of that baby is 240, you can see. The fuse is 15 amp. This circuit is normal operation condition of a circuit. It can run forever, right? Nothing. Look at that, 10 amp load here. I have 10 amps load coming out of 15 amp. It can run forever. That's your normal operation condition. Let's go to the overload condition. Now, I went to Adam, and Adam decided to put two microwaves. Here's microwave number 1. This is microwave number 2. He decided to plug another microwave from the same circuit. Look what happened. Now I have 24, two loads in parallel. You guys remember, I don't know if you did it with Gary or we did it with Polly, when you did two resistors in parallel. What happened if you put two resistors in parallel? You cut their impedance by half, right? So here's your, they're the same. So you cut the impedance by half. So the impedance here becomes 12 instead of 24. No problem, Chad. Take the 240 divided by 12. Look what happened to the current. Now my current is 20 amp. Now you're pulling how much? 20 amp out of how much? 15 amp. 20 amps out of 15 amp. You know what's going to happen to your circuit breaker or fuse? It's going to open. It's going to take a certain amount of time, maybe a couple of minutes. Bam, your fuse will open. This is called the overload condition. Any comments, guys, about overload condition? You overload the circuit. You basically double maximum. You double the load on that circuit. You double the load on that circuit. That's what we call it, overloading a circuit. Any comments, guys? Any questions? Now, if this fuse does not open, gentlemen, this conductor starts burning. Any question about overload condition? So here's your normal condition for a circuit. Here's your overload condition for a circuit. Let's go to the short circuit. Look what happened with the short circuit. Now, Adam was doing his work, installing this microwave, number 1, and he accidentally or intentionally took a wire and tied it hot to hot. This is hot 1, this is hot 2. This is a 240 system. Can you see that? And he went to take hot 1 and hot 2 and tie them together. Would you do that, Adam? Intentionally? I hope not. Now, if you do that, what happened to the load? Now, the load has been bypassed with a zero impedance. When you put zero impedance in parallel with a load, guys, what do you think you're going to get? Zero impedance, or approximately zero impedance. So this load becomes close to zero impedance, right? Or resistance, when the only resistance in the circuit becomes is what? The source as well as the cables. That's why the 0.001, this is the impedance of the conductor, it's very small. So if you divide this number, guys, by very small impedance, what do you get? You got yourself 80K, 80,000 amp, is that what we did? 80,000 amp. Gentlemen, you are looking, and ladies, you are looking at a short circuit condition. Can you guys see what a short circuit condition? That's your semi going at 110 miles an hour down Interstate 94 and hitting a brick wall. That 80,000 amp will do two things: shake and bake. It will shake your equipment, and it will bake it. Now imagine shaking. Can you imagine shaking a panel like this? What happened to the bolts? And it's going to loosen everything. It's getting off the wall. And imagine you being standing right in front of this piece of equipment when that happens. So that's the short circuit condition. Now the open circuit, the other condition, guys, is open circuit. Open circuit, it's not as big of a deal. Open circuit, Adam went there and cut the wire, grabbed the wire right here, and chopped it into little pieces. Now there is no current going in here. The current that's going here is 0 amps. Now this has an open circuit condition. That's another condition where the circuit's open circuit. Open circuit is like turning the light off. It's an open circuit condition. It's not dangerous. So when you put this one at the infinity, basically the impedance become here infinity, you get a 0 amps. That's your open circuit condition, open circuit condition. The ground fault condition, guys, it's not here, it's later on. The ground fault, if you take one of these phases to the ground, to the pipe, a ground fault, it will give you close to, under the worst scenario, 80,000 amps, but typically half of that. If you have a ground fault condition, typically half of what the three-phase short circuit. So if a ground fault condition, say maximum, will give me 40,000 amp in this circuit. What's a ground fault condition? You take phase A, tie it to the pipe, to the ground. Any comments, guys? Any questions about normal circuit, overload, short circuit, or ground fault, and the open circuit condition of a circuit? Any comments? Does it make sense? We've done some of these guys in the residential too as well. Okay, now moving on, because of all this situation, guys, we have to have, with short circuit, we talked about the short circuit is bypassed. They call it, when you have a short circuit condition, the load is being bypassed, and that's where the short circuit term comes to be, like we call it short circuit, because you bypass the load. And I don't know if Polly told you, Matt, when she taught you, I don't know who taught you, Derek, who taught you basic? Scott? Okay. Or Scott told you, when you have a load, parallel paths for the load, the current will take the least resistance, like a human being, right? If it's congested, the highways is congested, what do? You go bypass it and try to get away from the congestion. Same thing with the current. That's where the short circuit is. Okay, withstand rating for conductors. We talked about how much current these conductors can handle for how long all the time before they turn into charted pieces of copper and aluminum. Or aluminum. Okay, conductor heat. This, I'm repeating myself, guys. There's shaking and baking. The first thing happens when you have a short circuit or overload condition, it's the heating. The heating is expressed by this term, I squared T. What is I? Current. What's T? Time. I squared T or I squared S. I squared T, I is the current, T is the time. So take the current square, multiply by how long, it will get you how much heat this equipment is rated for. It's called I squared second or I squared time. It's a measurement of the heat radiated, guys, from the short circuit condition. Every time you have a current going through a conductor mat, you have a heat. But the heat coming out of a 10 amp is completely different than the heat that's coming out of a 1,000 amp, right? You see, it's 100 times more. That's why I squared T becomes huge. If you put 10 amps into it, big deal. Let it go for another, as long as you want it to go. But you put 1,000 amp in it, and your conductor is number 14. Now you're going to burn your conductor because you're going to generate more heat. The heat they generate in the conductor have to be radiated, guys, or convect away. And that's what happens typically if it's a normal operation condition. The circuit will heat up, the heat will dissipate, right? Radiate, dissipate, convect away from the conductors under normal operating condition. Short circuit condition, it's not enough time for the heat generated by the short circuit to dissipate. So what's going to do? It's going to sit there, cook the equipment. So then welcome to the I squared T. That's called the I squared T. The term that we use I squared T with it. Here's a good example, guys. If you have an equipment grounded conductor, this is just for a ground fault. If you have a piece of equipment here, and you need an equipment grounded conductor, this is my equipment grounded conductor. This is number 10, wire number 10 size based on this table for this conductor based on, I believe that we're using a 60 amp circuit breaker. Okay. So depending upon what type of a fuse you put on this conductor, you can cook that conductor. You can cook that conductor because of the withstand rating of this conductor. So here's a calculation that we need to do, guys. The calculation that we done for this conductor number 10. Now Adam, here's my number 10 conductor, like I said, 60 amps. Here's my equipment. Here's my equipment grounded conductor. I did a ground fault here. So I did a ground fault. The ground fault current, guys, is 246 amps. I came up with 246 amps. Now the question would be, I measured it. I came up with 246 amp ground fault. How much heat this will generate into the conductor? Look what happened. You take this I squared T, guys. You take the current. Can you guys see the current? And I want it for 5 seconds. 5 seconds. I want to see how much energy this conductor can handle for 5 seconds. Here's the current. Here's 5 seconds. I decided to use 5 seconds. I could use 5 hours if I want to chart it. So you take the current, you square it, multiply it by the 5 seconds. Gentlemen, this is the I squared second that you can get. This is the amount of energy that this conductor will encounter under these circumstances. This, how much current this conductor can encounter under these circumstances. Take the current, square it, multiply by how much time do you want it to stand? Typically 5 seconds, 5 seconds. If I say 4 seconds, multiply by 4. Nothing really into it. Now, if I ask you how much current, if I ask you guys, find the I for the same conductor, you take the 302, 580, and I want you guys to find the I, the current I, knowing that T is 5. T is 1 second. If I said, well, can you find me how much, this is for 5 seconds. This is for 5 seconds. Can you find me how much current this conductor can handle for 1 second? Look what they do. Here's what you do. You take this formula, guys. You flip this formula, right? And I hope you understand how you flip that formula, right? You take the square root of the amp squared per second divided by T. Here's the number that we came up with around a second ago. Divided by 1 second because Chad wants to know how much current this conductor can carry for 1 second. Gentlemen, a number 10 conductor for 1 second can carry 550 amps for 1 second. You put 2 seconds on that baby, what's going to happen? Completely burn it. So these are what they call the withstand rating for conductors. Conductors can carry, guys, current continuously. That's where you go 310.15B16. 15 amp for number 12 is continuously, right? Typically 12 and a half. Now, double this, that's overload for a couple of minutes. Now multiply this by 10 times, 20 times, 30 times. That becomes, it can handle it for seconds. It can handle this one for seconds. Okay, if you have a current limiting fuse, I'll show you guys a current limiting fuse. The peak lit through and the RMS lit through will be used in this formula, guys, to decide how much thermal and magnetic field will be lit through. They use something called the current limit fuse. The current limit fuse is very simple. You put 100,000 amp here. For a quarter of a cycle, it drops it down to 25. Right? That's it. It limits it. So why do we do that? Why would it do something like this? When it limits it to 25, then this equipment will not be shaken and baken at that much. So they use the current limit fuse that lit through the RMS, I squared T lit through is very small. Okay. For conductors, if you have a bare conductor, guys, bare conductor, in order to find how much current that conductor can handle, here's the rule that they use, and you guys don't need to know that because we have a software, but to use it, for 5 seconds, remember that magic number 5 seconds? Every 29.1 circular mil can handle 1 amp for 5 seconds. 1 amp for 5 seconds. So take the circular mil of your conductors, divide it by 29. That will get you how many amps this conductor can handle for 5 seconds. For example, if I have a 5,000 kcm, guys, kcm, there's a kcm, divide this baby by 29.1. Gentlemen, that will get you how much current this conductor can handle for 5 seconds. If you want it for 1 second, what do? Flip the formula again. I will get you how much it can handle for 1 second. Do you guys expect it to handle more for 1 second than for 5 seconds? Yep. For 1 second, the conductor will withstand, hold more current than for 5 seconds. How about for 10 seconds? Less. The more time, the less current the conductor can handle because you are being baken and shaken. The more you let that food being shaken and baken and shaking, the longer, the more you're going to damage it. That's how you find a conductor for if it's a bare conductor. If it's an insulated conductor, the value that they use is 26 something. 26. Same thing, 1 amp for 5 seconds for 26 circular mils. So if it's insulated, you divide this one by what? 26, if it's insulated. That's called the withstand rating of conductors, the withstand rating of conductors. When does the copper melt? Copper melting, guys, the value that they use for copper melting. Now we're getting withstand for, when you have a conductor, guys, you have two things. You have the insulation that's going to melt, and also you have the copper itself that's going to melt. So the copper, the calculation that they use for the copper, the same thing, that magic number 5 seconds, that magic for 5 seconds, that magic number 1 amp for 5 seconds for this circular melt, 16.19 circular melt. So if I want to see a 500 kcm conductor, how much will it melt? Divide this one by 6.19. That will get you how much current this conductor, the 500 kcm conductor, can carry before it starts melting for 5 seconds. For 5 seconds. So they use that withstand 5 seconds. If you size, what they're telling you guys for equipment around conductor, if you oversize the ungrounded conductor, oversize them for whatever, size them larger, then you have to proportionally increase the ungrounded conductor. Because if you oversize the ungrounded conductor, you will allow more current to go through during a short circuit condition. Then your ground fault conductors have to be proportionally upgraded, otherwise you will burn your conductors. And that's with your short circuit. Withstand rating is many engineers and engineering design like use tables, except we are using for all this is SKM PTW, the damage curve. All these guys, the nice thing, Adam, when you use the curve in a second ago, I mean, in a few seconds when I go through the software, you don't have to worry about this calculation. The software, you grab a conductor 500 kcm, and here's the damage curve for it. If your conductor is number 10, here's the damage curve for it. If your conductor is 1200 or say 1000, here's the curve for it, bigger. So, all this is, guys, have been tabulated by the smarter than Chad long time ago and put in the software for you and I to use through SKM and any other softwares. Okay, so that's so that now that we got the heat and how to calculate the heat, guys. Now there's the magnetic field. The magnetic field, yep, it is a square. The magnetic force, guys, is the smarter than Chad say if you take the peak, here's the peak of this signal, guys. If you take this value here, that's I peak, and you square it, Adam, not RMS. Here's the RMS. I RMS, root mean square, statistical value. If you take the peak and you square it, that will give you an indication, Karen, of how much magnetic force is going to be shaking your equipment. Baking it is the I squared T. The RMS I squared T. Baking is the peak, the I peak. So that's an indication of that one, of the baking, basically. The magnetic force that's going to, that's going to be moving your equipment. Arc flash and arc blast. With this, guys, come the two terms that we use, arc flash. Arc flash, your heat. That's how much, when you have an arc flash condition, guys, typically it's a high impedance short circuit. You have more energy released. That's going to burn the equipment. Blast, the expansion, that's a magnetic force, will get you an expansion of the heat. The heat will start expanding at a higher rate, and with it, take all that melted copper and throw it right into the electrician's chest. Bomb. You're talking about bomb condition, right? So ultimately, it will destroy your equipment. Now, Derek, not a big deal, can't afford it. But what happened to the bystanders and the electrician when it kills them and injures them? Now you're in a lawsuit. So that's what you see why we care about this, as an engineer, when you calculate them. If you don't put these labels there, it's a law, by the way. It is the law to have arc flash label on the equipment to put the energy that you're going to calculate. So we're the people from working on electrical equipment, energize, and the danger that could happen from the arc blast, arc flash, arc blast as a result of a ground fault or a short circuit condition. If you don't warn them, an average Joe apprentice would not know, oh, it's just go stick your fingers there, um, or drop the wrench there and arc flashes. So that's a law. Okay, magnetic force, summary of conductor short circuit. So clearing time, the amount of short circuit or ground fault, available clearing time of the. So all these guys is how much short circuit or ground fault is there, and what's the clearing time of the equipment. How much current and for how long? How much current for how long? I can't emphasize the withstand rating for equipment or conductor. It's related to how much current. Can you see that? And how long. These are the two terms, Derek, that you're going to be encountered all the time. How much current is not enough, and how long, Like everything else, guys, I can put pressure on you. If I want to pressure your hand, wrestling, or look at the games, any game, right? It's not enough for how much. Now, how long is more, because how long will emphasize the energy. How long, time, I can't emphasize. The current as well as the time is a major part on the arc flash condition. Okay. Any comments, guys? Any questions? That's basically the withstand rating for equipment, the conductors. Two forces, Karen. One of them is thermal force, or two factors. One of them thermal, that's the cooking, and magnetic, that's the baking. The baking and the shaking. The shaking would be the magnetic force, and the baking would be the thermal effect. I'm going to go over, guys, the tabs, the rule tab, conductor tabs. These are coming, the NEC code book, guys, says the conductor, if you have a 20 amp circuit here and feeding your beautiful light here, this conductor cannot be more than number 12, right? So you have to have an overconduction device at the point where the conductor receives its power, right here. Right? That's typical. That's almost 99% of the time. There is an exception for this. They call them the tabs. We'll talk about the tabs. The tabs is you take a conductor 100 ampere and you grab from here and you put your conductor right here. So let's just, I'm going to say 10 amps, 15 amps here, and you feed a piece of equipment here. So can you guys see the equipment received its power here? If you put 10 feet here, that's 10-foot tab. If you make it 25 feet, that's 25 feet tab. 25 feet tab. So can you guys see, here's 100 amp. Here's my conductor here is number 14, for example. And the overconduction device ahead of it is 100. There are rules in 240.21 that talks about the tabs. I'm going to summarize them in a second here. The rules for tapping, summarize them in a second. Overconduction device. Okay, overconduction shall be provided in every ungrounded conductor. Several exceptions for this one, for the tab. And this is just telling you guys the things that you know for feeders, branch circuit, and what's not. For feeders and for your branch circuit, if you have 100 amp panel, you put your number 1 here, right? You cannot put 1,000 amp here, can you? On a number 1. That's what you guys have done with me for branch circuits and feeders. The tab is an exception of this one. Service entrance conductor also have to be rated to carry the calculated load. You have just done the calculation with me to do that. What I'm going to show you, so that's basically it, guys, in terms of the calculation. Let me show you a couple of things here. We talked about the normal operation of the circuit. Derek, my friend, we said normal operation, everything is cool. Overload operation, can you guys see the current has doubled? The current has doubled here, fuse will open. Short circuit, look at that. You got 80,000 amps, within seconds the circuit breaker will open. Ground fault, here's what a ground fault, guys. You take the hot, touch the conduit, you got yourself a ground fault. That will be typically half of the 3-phase short circuit. Open condition, we talked about the open condition situation. Current limiting, if you have a current limiting, I'm going to talk about this one a little bit, guys. Look at this. If I have 1,000 amp, I want you guys to look at this. I have a 100,000 amp, If I have a current limiting fuse, look what happened. It takes this 1000 amp, take it all the way back to this current limiting fuse size and drop it down. Now look at this. It drops it down. It drops it down to, in this case, 4000. Can you just see what current limiting fuse is? It opens so fast that if you have a current limiting fuse, like I said here, and here's my equipment, I have a short circuit coming. If I have a short circuit, my short circuit right at this point is 100,000 amp. Right at this point, as it moves through this, it will drop it down to 4,000 amp. Who cares? Who cares when it drops it down? Your equipment will not be shaken or baking as much. Okay, so that's this is shaking. Now the baking, guys, if you continue with these, now for the baking, we're not showing the baking. If you continue with this one, that's how much. So that will be get you, if you continue all the way up to here and all the way to here. So what would that be? 200, 300. So that will be 350,000 amps here. It will drop this down one to here, which is 808. So that will be 9. So 9,000 amp. So look at that. The baking current dropped from 1,000 to 4,000, 100,000 to 4,000. The shaking dropped from 350,000 peak all the way down to 9,000 peak. Who cares? Anybody can tell me why we care? Your equipment, guys, will not burn. That's all. So the smarter than when you hear a current limiting fuses, remember that it limits the current. It drops it down. How do they do that, guys? They drop it. They open the fuse or circuit breaker so fast. They open them so fast that it will basically limit the amount of energy. It will limit your amount of energy. Any comments, guys? Any questions about the current limit fuses? We will talk about current limit fuses, guys, as we go in the industrial. You will hear a lot if you in the industry, if you start in this industry too. This is really interesting, Adam. Look at this. If I have a 10,000, this is, can you see that this is a 40,000 amp? I have a 40,000 amp, gentlemen, a 40,000 amp. If I want the 40,000 amp to open within 1 second, can you see 1 second right in here? The conductor size, it has to be for 1 knot. Can you see that? The conductor size, that's a damage care for conductor. The conductor size 1 knot. If I allow the conductor to go all the way, just say to this, which is 30 cycles. If I allow the conductor to go to 30 cycles, it goes all the way down to here. So you're, I don't know, maybe 600 kcm. If you set your fuse, guys, to open at 30 cycles is half a second. Your conductor have to be upgraded to handle it from 1 knot to 600 kcm. One day, gentlemen, you will appreciate that one if you guys do short circuit analysis. So anyway, what I'm going to summarize, guys, is the faster the circuit breaker trips, the better for your equipment. Or the fuse open, the better for your equipment. Typically, we trip within 3 cycles. 3 cycles. In a quarter of a cycle, if it's current limiting fuse, is quarter of a cycle. If it's circuit breaker, within 3 cycles. Any comments, guys? Any questions? So that chart will show you one thing. The longer you want to allow the short circuit to sit in your system, the bigger your conductor have to be. Current limit fuses, Adam. Here's a short circuit condition, guys. Here's the peak. Can you guys see that offender? The peak here is responsible. My peak here is responsible for the shaking of my equipment. Can you guys see that? My peak is responsible for shaking my equipment. If you have current limiting fuses, it will open so fast within a quarter of a cycle that only the amount of energy that allowed to be seen downstream is this amount of energy. Can you guys see that? Why current limit fuse is limited? They allow you to, this is the amount of energy that can get. Versus if you don't have a current limiting fuses, all this will be the amount of energy that your equipment will be encountering. Who cares? One word, Karen. Your equipment will not be shaken or baking as much. Your equipment will not be shaken or baking as much. Any comments, guys? Any questions? Any comments? Any questions? So when you see a current limit fuses, how you can open it so fast, so your equipment will not be shaken or baking as much. Okay, the last thing I'm going to talk about, guys, before that one is talk about the rules, the tab rules. I want to bring your attention, guys. I have a 600 kcm disconnect that bring it to a gutter. From this gutter, I went to a 60. I have a 10-foot tab. Can you guys see that? That 10-foot tab. And I went into a 60 amp circuit breaker. And I have a 25 amp tab. And I went to 200 amp circuit breaker. Can you guys see that? You tab the conductor. You tab the conductor. The length. So the rules for the tab are summarized right here. I'm going to go ahead and summarize what the rules when you do this. Can you guys see the rules? Oops, not here, Chad. The rules are very, very clear. Number one, the length cannot exceed 10 feet when you tab. The calculated load cannot be more than the conductor size. The calculated load cannot be more than the conductor size. The overcomputation device have to be landed on overcomputation device. The conductor cannot be less than 1/10 of the ampacity, and the next standard higher does not apply, and you have to put them in a raceway. These are the rules for a 10-foot, to use a 10-foot. Very simple. If you guys look at the one underneath it, the 25 feet, the same thing. It's 25 feet, no more than 25 feet, 1/3 of the overcomputation device. You have it has to be rated, it has to land on an overcomputation device. You can't go to the next standard, and you have to put them in a raceway. You have to put them in a raceway. I'm going to use the 25 feet rule here, guys, and show you how they do this calculation. So the first thing, when you have a 25-foot rule, when they tab, so remember, the overcomputation device right here is, how much is the overcomputation device here? The overcomputation device 600. Can you guys see that? This is 600. So when you have a 600 and you need to tab a feeder, that's 600 amp feeder, 25 feet, you take 1/3 of 600, gentlemen, what would that give you? 200. So this conductor here has to be 200 amp. The smallest conductor, 200 amp. It can't be 150 amp. So go to 310.15p16 and find me a conductor 200 amp. That would be 2 watt. Would that be, what did we size it? That would be 4 aught. Say 4 aught. AWG. Then you have to fuse it with the same amount of current, guys. Here's 200. You put a 200 amp here. You have to fuse it. You have to put it in a conduit. Here's rigid metal conduit or EMT. Rigid metal conduit or EMT. You have to fuse it. It cannot be longer than number 25, longer than 25. So that's basically the rules for the 10-foot or 25 feet. Any comments, guys? Any questions about the 10-foot and the 25 feet? You will hear me talking about these guys in the spring, the same thing, and after that, you're on your own. So I can't emphasize, there's a lot of good information, guys, in these chapters. A lot of information, though. You can handle as much you can at this point, but okay, so the load that we feed from here, when you put a load right in here, cannot exceed the 200 amp. The load cannot exceed the 200 amp. That's the rules for the 25-foot rule. The 10-foot exactly the same, except is 1/10, the multiplier. This is giving you guys this chart will tell you that based on how fast the fuse will open, the conductor can be, so for example, if you open within a quarter of a cycle, this fuse at this amps, if you open within 1 cycle, the size has to be this way. If you a quarter of a cycle, your size will be this way. So 1 cycle breaker you're going to get this size. So anyway, based on how fast your circuit breaker will open, you will end up with a larger or a smaller size overcome protection device. Any comments, guys? Any questions? Any comments? Any questions? So I hope this, Karen, will tie into what we're going to be doing in a second here, which is SKM PTW, short circuit calculation. This diagram, Derek, is really nice because it summarizes the rules for the tab. What is a tab? A tab, when you take a bigger conductor, can you guys see? Here's number 10 conductor here. This is probably number 6. Number 6 conductor, and you're tabbing it from 600. Oh dear. Let's just say, let's say two sets of 500 kcl, maybe a little bit more. So you take a bigger conductor and you tab from it a smaller conductor for 25 feet. Then you put the overcome protection device. Any comments, guys? Any questions? Any comments? Any questions? Okay, I want to give you guys maybe 20 minutes, maybe 15 minutes until 9 o'clock. Then I'm going to start SKM. So do me a favor for SKM. I would like you guys to have the following handy and open. Your load calculation that you did with me, the sheet that you did for load calc, have it open. We need that. Have the riser that you did with me open. These two must be open. The riser that you guys did in Revit and the load calculation, so we can do SKM. Thank you.